So we learned about section 5.5, complex eigenvalues, last time. And, you know, complex eigenvalues are important, just like real eigenvalues are important. There is an example I want to discuss with you. It's example 2. So let me go ahead and do that. Let me find it here. Okay, so here's another problem, just like the one we did, where you have to find the eigenvalues of A and find a, example 2. Hold on, example 2, section 5.5. Okay, there's your matrix A. Find the eigenvalues of A and a basis for each eigenspace. So they go through the same process, and they get eigenvalues of 0.8 plus or minus 0.6i. They get conjugates. I mean, of course, eigenvalues will occur as conjugates. And then they go through and they solve for the eigenvectors. Okay, and we learn that when we have a system of when we try to find the eigenspace corresponding to the eigenvector, the system of equations we get, like for 2 by 2, we get 2 equations, but they are redundant. We only need to use one to solve. And in their case, they use the second equation and solve for x1 in terms of x2. So x1 was negative. Let me see here. One moment. So see, they're leaving out work. They're leaving out work. No. Wait. No. 0.75 x1 equals negative 0.3 minus 0.6i x2, and then they divide by 0.75. But then, of course, in decimals, eliminating decimals and having eigenvectors with integers is always important. You'll see in the homework for section 5.5 that they want that. I will get that posted very soon. The first eigenvector is here. Now, given that's one of the eigenvectors, what's the if one eigenvector has components negative 2 minus 4i and 5, what's the second eigenvector going to be? What's the second one have to be? So you have a complex eigenvector. That's right, Solomon. That's right. The second eigenvector would be negative 2 plus 4i for the first component, and then a 5 for the second component. Very good. Very good. And, there it is. There it is. Okay, hold on one moment. Oh, wait, there's a question. Hold on, let me go back here. Okay, all right. Well, good to see you, Moshe. How do we know that? How do we know that, Matthew? Because, well, I mean, you can use brute force and calculate that the second eigenvector is negative 2 plus 4i and then a 5 for this second example from section 5.5. But it always is it's mathematically the case that eigenvalues occur as complex conjugates, and the eigenvectors, will occur as complex conjugates when you have, complex eigenvalues. So it is just, it is the case that is true. I've never really formally seen a proof of it, but that doesn't mean there isn't one. But for now, let's just take it on faith. And then they do point something out here that in example 3 here, let me find in example 3, they talk about how if you multiply 0.8 points, like x sub 0 is 2, 0. Well, if you take x sub 0, multiply it by 2, if you take that initial value of 2, 0, that initial coordinate, and multiply it by a, you're going to get x1, and that's going to be 1.0 and 1.5. Then if you take x1 and pre-multiply it by a, you get x2, and that's going to be negative 0.4 and 2.4. And you can keep doing this. And you'll notice that when you do this these transformations, it causes the points to be rotated. So they show in this figure coordinates. So like the first coordinate was 2, 0. So that's right there on the x1 axis. The next coordinate is 1.0, 1.5. Well, that looks about right. Okay, and then the next coordinate is negative 0.4. You know, the x2, I should say the x2 vector is negative 0.4 and 2.4. There it is. And so what happens is it turns out that the act of multiplying the vector by the matrix A is a rotation. So every time you multiply a vector by a point, you rotate the point, and you get this ellipse, this elliptical shape. Okay, and this is really well, you get there's a theorem 9 that talks about it, talks about why this is true. But I think I want to get to this example 6, because this example 6 really shows you why it's true. So I want to be a little bit careful. It's not completely why but if you have a matrix C, okay, with components along the one diagonal AA, and then negative BB, where A and B are not both 0, then the eigenvalues are going to be A plus or minus BI. So you could use the quadratic formula and show that. Okay, but that means then that the magnitude of the eigenvalue, is square root of A squared plus B squared. How many remember when you I don't know if you've seen this, but if you have a complex eigenvalue, you can get its like modulus. You can get its like length. Like, well, here in the picture in figure 2, here in the figure they plot the coordinate AB, so that's like A plus BI. You have on the horizontal axis the real numbers, and on the vertical axis the coefficients of the imaginary I part of the complex number. And so R is the square root of A squared plus B squared. But you see, what you can do then is you can write the matrix C. You can write the matrix C this way. You can write it as R times that matrix there, where you have A over R, negative B over R, B over R, and A over R. You can do that. But then, very interestingly, is you can split that transformation up as a composite transformation, where the matrix on the right, the first thing you do is you rotate the points. Like if you multiply that matrix C by a vector, first thing you're going to do is rotate the points by an angle, by that angle, eta. That's an eta symbol, and I believe it's an eta. You have to. Gosh, I haven't seen that symbol in a while. Let me see. Is it maybe phi? Hold on. Somebody might know. Let me see. The symbol phi. That's it. Yeah. Right here. Right here in that matrix, that's a phi. So the angle phi is the argument of, like, if you plot the coordinate AB, phi is your reference angle. And so you can interpret the transformation where you take the matrix C and multiply it by the vector x as a composition of a rotation, but then there's a scaling. You scale that as well. And it's an interesting observation, So they basically I want to say this the right way, but like see the like for right here, the cosine of phi. The cosine of phi, of course, cosine is adjacent over hypotenuse. So based on figure 2, the cosine of E is A over R, right? X over R, A over R. And if you take, I want to do this right. Now, one moment here. No, okay. Let me see here. One moment. Yeah, that's right. If you take then, let me just, if you take R, so what I want to do here, let me be very clear. Let me justify this first part here. So in the top left-hand corner of the matrix C, you have the variable A, or the number A. So when you do the matrix multiplication, is R times the cosine of phi equal to A? Well, it is, because cosine of phi is A over R. So R times A over R is A. And you can verify the rest of your entries here just like that. So it's pretty cool. It's pretty cool then that the transformation by taking the vector x and multiplying it by c, it's a composition of a rotation through the angle phi and a scaling by the magnitude of your eigenvalue. And there's a little picture. There's a little picture there. And there's another theorem here. There's another theorem too at the bottom, where it's theorem 9. You know, I want to try not to get too technical, but they're saying, suppose you have a 2 by 2 matrix with a complex eigenvalue lambda equals A minus BI. Well, the matrix A can be it can be written as A equals P times C times P inverse, where the matrix P consists of the real part of the eigenvector, corresponding eigenvector, and the imaginary part of the eigenvector. So like what they mean is that like if your eigenvector for like that example we looked at, example 2, the eigenvector was negative 2 minus 4i and 5. Well, negative 2 and 5 form the real part of the eigenvector, and negative 4, 0 is the imaginary part. So that's how they're constructing P. That's how they're constructing P. And this is proven in the exercises 25 and 26. So it is possible you'll see that in your homework. But it's an interesting result. It is an interesting result, and you know, one noteworthy of sharing with you. Are there any questions on that at all? Are there any questions? All right. Well, then I'm going to go ahead and stop the recording on this, if we're good. Very good, Matthew.